Okay, so we're kind of going to do an overview of quadratics, or a quadratic overview. That makes more sense. So this here is a quadratic function, or at least a parent function. They call it parent function because these coefficients, the a, the b, and technically c is a constant. I just have variables in there. I don't have an actual number, so I can't graph this. I need actual numeric values in order to put this on a graph. But the general form of the function is standard. We tend to write them this way. In fact, this is literally called standard form. And you'll notice with quadratics, there's going to be three major forms you're going to work with. So there's the standard form. There is, I'm going to write another one here. This one is called the factored form. And you'll see it's usually two sets of brackets with an x. And they may say like minus r, minus s, minus m, minus n. It doesn't really matter what letters or variables they use to represent it. But this is a different form of a quadratic. And the third one you tend to work with is the vertex form. And a lot of times they'll use letters H and K. Sometimes there's like a D or a C they use. But again, those letters, when I say these letters, these variables, H, the K, the A, the S, the R, A, doesn't matter what letter we use. It's just representing a form of a quadratic. And each of these forms has something that's really important, or at least very, very helpful in terms of graphing. The standard form is, you'll see most quadratics written this way. When it comes to graphing, it's actually not a very good form to look at at all. It doesn't help us very much. It's the C value here, it'll give us one thing. It'll give us the y-intercept of something, okay? This one, the factor form, I guess I should give them all titles, because that would be nice. Right? Let's call this standard, so we know what I'm referring to. Factored in blue. And this one is called vertex. The factored form, the r and the s, they give you what the roots or the x-intercepts are. And usually it's the opposite. If it's like plus 5, then one of the roots is negative 5. And finally, vertex, what's nice about it is the h and the k, they represent the vertex of the quadratic. So if I were to draw, let's just say that red is, let's go black for it. Oh, I don't want that. I needed to do something else. There we go. So say we have a quadratic like this, okay? Each of these forms will give us a little bit of information about it. So this point here, this is your y-intercept. I didn't make it either. Intercept. That's actually this one here. This value, the c, the constant in the standard, will tell you what the y-intercept is. You can literally look at that and plot that point. That's very helpful. The x-intercepts, and there are usually two. It's possible to have one. If you had a quadratic like this that just touches the line, you would have one. They're a little rare. And it's possible to have quadratics that have no roots, like they're floating above or floating below, in which case there's literally like no form for that. Those are possible, but again, rare. Your factor form, the r and the s, they literally give you these. So these are both x-intercepts, okay? Intercepts. And then finally, oh, I changed the color. That's what happened there. And finally, in green, oh, I used green twice. I guess I'll do this one red. The vertex, which is also known as like the max or the minimum. It's a minimum if it's facing upwards like this, because it's the lowest point. If you have a quadratic that's facing downwards, then this would be considered the max because it's the highest point. We don't need it though. There we go. That is, or the coordinate of it, is actually like your h value and your k value. So these values right here, they tell you what that is. So depending what form you're in, you can find out a whole bunch of information about the quadratic. Now it's a little easier to work with an actual quadratic, so what I'm going to do is we're going to put a quadratic here. I'm going to start it in factor form. And the reason I'm going to do that, and I can actually write f at x. I guess we should talk about that. I didn't even speak to that. Let's go back. F at x. There we go. F at x equals. I'm going to put it in factor form. X minus 3. X plus 5. Let's go and zoom out a little. Okay. Nice. Oh, great. I got whole values. I was kind of guessing at that one. Okay. I put this in factor form. You can see in like the top left here. I can compare that to our other page, and we'll talk about what they all mean. So f at x is literally the same as writing, and I'll show you in Desmos. It's actually the exact same as writing y. It's just called function notation. Y equals, I'm going to write the exact same thing. You're going to see it's going to overlap. X minus 3 and oops, x plus 5. There you go. If you notice, we're going to turn the color on and off. It's just overlapping. They're the exact same thing. So f at x and y, literally no difference in terms of that. What it is doing is f at x allows us to take stock of like values we're putting in for x. So for instance, if I were, let me just jump to another page really quickly to do this example. If I were to have the exact quadratic we just talked about, I think we said x minus 3, x plus 5. Let's say I wanted to find the y value when x is equal to, I don't know, 10. The way we would write that, instead of like writing a whole sentence of saying like the y value when x is equal to 10, this notation allows us to just go f and we put bracket 10. And 10 is replacing that x value. So that communicates the concept that, okay, we're replacing x with the number 10, and now the rest of the equation, I'm going to plug in the number 10 for all of it. Okay, that's all function notation really is. They might have shown you a couple other things. Have they done like ovals to deal if something is a function, anything like that? Yeah. In order for something to be a function, so we've kind of gone off track, but that's okay. Every x coordinate can only have one y coordinate. There can only be one y coordinate, right? So if I say I'm at here, so I have a coordinate like the x value is 2 and the y value is 5. Okay, I can't have another coordinate where the x value is 2 and the y coordinate is 3. Okay, this can't happen. Otherwise, this is no longer a function. Okay, so when they talk about function notation, it's things that essentially, if I have a quadratic, I can draw vertical lines through. And if I could draw a vertical line and only have one point that touches everywhere, then that is a function. If I have something like this, see how I'm starting to get 2 points when I draw those vertical lines? This is not a function. Okay, they represent it in different ways, like with these ovals, they might represent it as like a domain. The domain is x, or the domain is like 3 and 5, and then the range is, I don't know, 2 and 1. There's so many different ways to represent it. That will be really specific to this chapter. As the course moves on, really, this is all you need to know. This part right here, where you're f at x, and we replace x with a numeric value, and all that means is we're plugging in a value for x. That's all it's talking about. What you're saying is this function, sorry, let's start here. This function has the variable x in it. That's essentially what it's trying to say. Okay, does that part kind of make sense?
Yeah.
A little bit? Okay.
And then you would just solve for it?
Yeah, you could just solve for it. A lot of times what it is when we write in function notation, I can write a linear function. We have mx plus b. All that is replacing y. It's just function notation. Instead of writing the letter y, we just say, if we're writing in function notation, we'll write f at x. I could write g at x. And what that's telling you is whatever I'm going to write here is different from this function here, because this is g, and g is not f. We're honestly getting even too complicated for your course. You probably won't even get into that concept yet, okay? But that's all it is. It's just a style of communicating in mathematics. But back to here. So we have our quadratic, and if you take a look, we have x minus 3, and one of the roots is positive 3, and x plus 5, one of the roots is negative 5. So like I said, it's just kind of the opposite operation of what those two numbers are in the brackets. So what's really nice is factor form gave us our two roots really, really quickly. I'm going to go back to this page here. So I'm going to write that in. We had f at x, we had x minus 3, write in blue so it matches, and x plus 5. Okay? Now, if you notice, there's no value here for a. And if there's nothing there, we actually just assume it's the number 1. Okay, so the a value is 1. A deals with stretching. I don't know if you remember that stuff, stretching and compression quadratics. You'll get all into that transformation of functions, but for now we'll just focus on our quadratic stuff. So I have the factored form. I need to find the standard form. And to go from factored to standard, you expand. Technically, you expand and simplify, but we're just going to say expand in this case, okay? So, actually, we'll jump to another page here. So, we're going to go about expanding. There we go. So we have the function f at x is equal to x minus 3, x plus 5. And technically there's a 1 here. We'll even write that in so we get used to it. This 1 I can distribute into both of these. 1 is going to change literally nothing, hence that's the main reason we really don't write it in. You're still going to be left with the exact same equation after you distribute, because x times 1 is x and x times negative 3 is negative 3. Next, what you're going to do is distributive property. I think you may remember this. Sometimes they call it like the FOIL method or rainbow method. Essentially what you're doing is you take this term and you multiply it by both terms in the other bracket, and then you take your second term and repeat. You multiply it by both terms in this bracket. So we're going to go f at x is equal to x times x, so we'll do what I have here in blue. X times x is x squared. X times positive 5 is 5x. And then negative 3 times x is negative 3x. And negative 3 times positive 5 is negative 15. So we've expanded. This is technically the simplifying part now. The simplifying part is we have to find, looking at these 4 terms, any terms that go together. So we look for variables with the same exponent. So x squared is the only one. This one, both of these variables are technically to the power of 1, so they'll go together. And this is a constant, and it's the only constant. So those two are going to stay the same. So we go f at x is equal to x squared. We'll combine the two middle terms, so we just look at the coefficient, plus 5 and negative 3, so we do integer math. So positive 5 minus 3 is going to give us positive 2. So we say plus 2x, and then the other term, negative 15, that stays the same. And we are technically in standard form now. There is an a here, x squared plus bx plus c. This is our c value, this is our b value, and our a value, if it's not there, it's 1, right? Which is the exact same as the other one. Great. So I should be able to put this function into Desmos and get the exact same graph again. That's what we're going to do. We're going to use Desmos to kind of check our work as we're going through stuff. So x squared plus 2x minus 15. So let's see if we got it. So I'm going to do function notation again. F at x is equal to x squared plus 2x minus 15. All right, and if we turn off the green, it overlaps the blue. These are all the exact same. Perfect. That means we have the same quadratic, just in a different form. So right now we haven't used any different quadratics. We've worked with one in factored form and one in standard form. The other one that we're going to deal with, let's go back, is our vertex form. So vertex form, there's a couple ways to go about this. Because we already have factored form, we can go to vertex form from there, or we can go from standard form. It's common in your math class, they'll teach something called like completing the square. Technically, there's little equations you can use instead of that very long process. It's also, we can go from our factored form to vertex. And I'm going to show you that because it's a bit of logic instead, and completing the square is a bit of a long process. So we're going to do the easier route. We're going to go from factored to vertex. So I'm going to go back to this factored form. So still, you might hear knocking for a bit. X minus 3, x plus 5. Okay, we know from looking at this that one of our coordinates is negative 5 and the other one is 3. Hey guys. Sorry guys. So we have our quadratic, we have two roots. We know that actually the vertex is right in the middle of the two. So instead of doing a process, we just do averages. Something to be right in the middle would just be the averages of two values, so negative 5 and 3. They'll call this the axis of symmetry. E-T-R-Y, I think that's it. Spelling is not my forte. But axis of symmetry, what you can do to figure that out is you take your R value and S value. If you remember, your factored form is written like this, x minus R, x minus S. So we take these two values. So we take the R plus the S and we divide it by 2. That's the axis of symmetry. Sometimes a teacher might write it like this. AOS is equal to R plus S divided by 2. This might be like a small formula you'll see. If they haven't, that's okay. It's a helpful one, though. It's very helpful for what you're going to do. The logic to it, again, is just remember, you have two roots. We're just trying to find the dead middle of them. That's how we find the vertex of anything. As long as you have two coordinates that are on the same horizontal line, we find the average, and we can find out where the x value of the vertex is. So we'll take our R, which is -3. So we have -3 plus 5 divided by 2. Well, -3 plus 5 is 2. And 2 divided by 2 is 1. So this should be at the x value of 1. Hopefully that's right. This is a very terrible sketch, so it's not to scale. But what that means now is our x value of our vertex is 1. We don't know the y value. This is where function notation is really helpful, actually, for discussing what the next point is going to be. So what we're going to do now is we still have our factor form. We're going to take f at 1. We're trying to figure out what the y value is when the x value is 1. So I'm going to put it into this equation. So function notation is saying take 1 and replace both of your x values with the number 1, and that will tell you what the y value is at that coordinate. So we're going to say 1 minus 3 and 1 plus 5. Okay? 1 minus 3 gives us -2. 1 plus 5 is 6. -12. So according to this, our vertex is at 1 and -12. I can jump into Desmos to double check that. I can literally click on it. Oh, 1 and -16. Did I do my math wrong? 1 minus 3, -2. What did I do wrong there? This is good at Desmos. It'll tell us what we made a mistake. So I have made a mistake, but where did I make the mistake? 1 minus, that's -2. That's 6. Let's make sure we got the right. Oh! Here's my mistake. This is good. Thank goodness for that, Desmos. See how one of my x values was -5 and one was +3?
Mm-hmm.
When I plugged it in here, I put -3 and +5. I wrote them backwards. If I wrote them properly, they should have been -5 and +3 and added them two together. Should give us -2, which would have given us -1, which means the coordinates should have been over here. Remember I said this was a rough sketch. It wasn't wonderful. And if this is -1, we plug in -1. It's going to change our values. This will be 4, and this will be 4, which will give us 16. Okay, so it's great. I found my mistake. We checked on Desmos, -1, -16, great, but how do I build vertex form? Well, vertex form, let's shrink this a little because we want on the same page. Vertex form is written at f at x is equal to a x minus h plus k. Well, the h value is the x value of the vertex, okay? So I'm just going to replace it. Let's say f at x equals a x, and the x value is -1. So it's actually -1. Okay? So -1 could be simplified. You know what it would be simplified into? Just +1. Okay? Think of it as a negative and a negative, make it positive, okay? The y value is -16. We're just going to replace k with -16. The only thing we're missing still is our a. Do you remember what our a value was before?
1.
1. So it's going to be 1 again. Okay, so x plus 1 squared minus 16. This should be the vertex form of our quadratic. We're going to plug it in, and we're going to double check. And if it is,
Daddy, this.
Okay, guys.
I put this in there. Maybe practice. Nanny?
Okay, f at x is equal to the a value is 1, so we say 1 bracket x plus 1, I believe, squared minus 16, and the purple overlaps.
So you just leave it like that?
Yeah, so all I was trying to show you there is I really didn't show you any like processes for solving things. I was trying to show you an overall
like how to get it.
Yeah, how to get to your different forms. You have 3 major forms, and there's different ways. And like technically, to go from vertex to standard, there's another thing. To go from vertex to factored, there's another. To go from standard to factored, you factor. There's different ways. But I wanted you to be aware that there are 3 major forms of quadratics, and everything you're doing is really just moving from one to the other because each of them give you different information. So another reason you might, actually we'll keep it here, another reason you might want to look at vertex form, because they might ask you for a max value or a min value in a problem solving question. If they ask you for the roots of something, well, we know we've got to get the factor form because that's what we're talking about x-intercepts there. Okay, they really don't ask for standard form. It's not the most helpful form of stuff, but it's very common to start in standard form. That's why it's important to know that from standard to factored, you factor, and from standard to vertex, you complete the square. Those 2 processes become really important. The other way you could do it is technically the quadratic formula. That'll take you from standard to factor and give you roots. But all problems with quadratics talk about max and mins or like roots, solving the quadratic. That's what you're trying to get at, okay?